So the calculations for single slit diffraction are all fairly similar. So I'm just going to do one example with two parts and we'll call that good. Here is the example. We have 620 nanometer light falling on a slit of this width, and we want to know the full angular width of the central diffraction peak. So what we mean by that is if my screen is over here and we've got a little peak and then our big central peak and a little peak, so my slit is over here somewhere. I want to know the angular width of this guy, not the actual linear width in meters or whatever. So I want to know the angle from here to here. So the boundaries of this central max guy here are defined by the dark spots on both sides. So we're actually going to use the equation for dark spots. If you remember, that was d sine theta equals m lambda. And we use a capital D for the slit width for a single slit. We have a lowercase d for the slit spacing on double slits, so we need to be careful with that. Well, I also wanted to mention the equation we had for bright spots, I'll just put it over here kind of out of the way, was d sine theta equals m plus a half times lambda. Now this gives you the location of all the bright spots except the central bright spot. We would need this to be 0, right? And we can't really do that when we're adding a half. So this is for all the bright spots after the central bright spot. And the central bright spot is always located at 0, so there's not really any calculations you'd ever have to do unless you want to know how wide it is, and then you jump to this calculation. This was approximately equals, by the way. Alright, so let's start writing down the information we know. We've got lambda is 620 nanometers. A nanometer is 10 to the negative 9th meters. We've got the slit width, so that is capital D, 0.056 times 10 to the negative 3rd. If you like moving the decimal places, feel free, that's no problem. And we're trying to find theta. Now theta in this case though, it doesn't give us this full angle here, it's going to give us half the angle. That's going to be our theta. So the full angular width is actually 2 theta. That's what we're going to find at the end, but that's easy enough. We find theta and double it, right? Alright, so we can go ahead and plug in. Oh, and because this is the first dark spot, then m, squeeze that in up here, m is equal to 1. So that guy you can just kind of ignore. So if we start plugging into this equation over here, where I've got some room, 0.056 times 10 to the negative 3rd, sine of theta equals, oh yeah, no, I thought I screwed that up and mixed up my numbers there, but we're good. 620 times 10 to the negative 9th. Now if I'm going to solve this guy for theta, I need to divide that to the other side and then take the arc sine. So theta is going to be the arc sine of 620 times 10 to the negative 9th over 0.056 times 10 to the negative 3rd. Throw that guy in your calculator and you get 0.634359. And again, we don't want just theta, we want the total width of our central bright spot. So we're going to multiply this guy by 2, so 2 theta is going to round to 1.27. And this is going to be in degrees, as long as you have your calculator in degree mode. So that is the angular width. And this doesn't depend on the distance to the screen, because these are angles and it's going to be the same no matter what. Now here, for the second part, we want to know the width of the central maximum in the diffraction pattern on the screen. So you wouldn't talk about having a screen and saying, well, I've got this bright spot here and it's that wide. So you wouldn't measure that as an angle. Here we actually want the distance in meters or maybe centimeters of the width of this. So what we want to do is think about our triangle here. We've got the angular width, and now we've got the distance to the screen is 4 meters. So this here is 4. Now I don't want to use this full width here. What I want to do is jump back to theta. So this guy here was 0.634, and I want to find this distance here from that angle, and then I can double it to find the full width. You don't want to use that full angle there because then you're not going to have a right triangle. So anyway, we've got our angle here, we've got our length of our adjacent side, and we're trying to find our opposite side. So relating opposite and adjacent, we want to use tangent. So we've got tangent theta equals opposite over adjacent, and in our case that gives us tangent of 0.634. Now I'm only writing those 3 digits, but in my calculator I kept all these digits and then some. Opposite is what we're trying to find, that's x, the adjacent of this little triangle here. So essentially we're ignoring the top part of this triangle for now, right? Go away, top part. Oh, not bottom part. So we've got this triangle here we're working with, that's x. Forget this little line here. Alright, that's 4, so x is going to just be 4 times tangent of theta. That comes out to be 0.0443 meters. And again, we want the full width of the slit, so we're going to multiply this by 2x, and we're going to get 0.0886 meters, which, if you prefer, you could say that's 8.86 centimeters. And so if we have a screen at that distance away, that's how wide that central peak will be. And that's all there is. See you next time.